Alright, let's keep going. Chapter 6 is going to be testing the atmosphere and specific gases in the atmosphere, just to make sure that you are aware of all the different types of exposures. So in this chapter we'll talk about some of the equipment it takes for testing the enclosed space. Talk about the different type of gases that you'll be exposed to, and of course I don't know all the gases, so I'm just going to give you some typical gases that may be there, but you, in the competent person, should know the specific gases that are going to be in your atmosphere for your type of entry. Then talk about the term, specifically vapor density, and then understanding the nature of common gases found in the permit required confined space, and then protocol for testing. So what happens when you're in a confined space? You have different hazards, and they could be previously stored products or chemicals. The manufacturing process could produce some of these chemicals themselves. Could be some work being performed near where the entry point is. So therefore, you should know that there are three different types and three different stratospheres, if you will, of hazard layers of gases that you'll have to look out for. So very top layer are those gases that have a higher, or I should say a lighter vapor density, meaning the physical weight of the vapor gas itself, than air. So your atmospheric oxygen is in the middle, what we're breathing. If it's lighter than air, you may have heard that term before, then it's going to be higher than where the level of atmospheric oxygen is, and then it is lower than air, heavier than oxygen. Then you're going to have your sulfides that are going to be in the bottom of the actual space. So again, there's three distinct stratosphere. Upper level is going to be more explosive gases. Middle layer is going to be more of your breathing air, and then lower level is going to be the same vapor density as, or I should say, it's heavier vapor density than your breathing air. So atmospheric testing, you truly want to, there's two distinct purposes. One is you want to evaluate that hazard in the space and then verify the acceptability to make sure that you can go into a space. So it's going to give you some quantification. When I first got started in the business, I was doing sewer entries, and they would say, young man, if you see roaches, go in. If you don't see roaches, don't go in. And that was it. I don't know what concentration of gases they are by roaches, so it didn't help me much. But truly, when it's actual calibrated meters, it's going to tell you a value that comes back to you. So there are 9 rules in atmospheric testing, and I'll make sure that this is going to be able for you guys to download them. But you want to monitor in the proper order for any corrosivity, your oxygen level, flammability, and toxicity. Those are the things that you really want to make sure that you're monitoring for. 2, you want to monitor the vapor density. So something that is the same level of oxygen is equal to oxygen. So you'll see a 1.0 vapor density. If it's heavier than oxygen, it'll be 1.1, 1.2, whatever, 1.05. And if it's lighter than oxygen, then you'll see 0.9, 0.8, 0.7 in round numbers. And now it's going to be lighter, so it'll be in the upper atmosphere. So know your monitor's limitation. So you have to really be familiar with your meters. Your meters will have known triggers, which is going to give your alarms. So at those known values, then it's time to get out of that space. You want to monitor your operating parameters, so you have to know know your monitor's operating parameters, and then understand that the flammable gases are also toxic. So you may have a condition where there's flammable gases there. You might also need to wear a respirator at that point. Understand that some vapors migrate towards the exterior of spaces, so therefore there might be an accumulation of these gases once you open the space. And if there is a spark, then now you would have the complete triangle of the fire triangle, where you'll have the oxygen, the fuel, and the spark. So just be careful of that. And then zero, inspect, and field calibrate meters that monitor that with clean air. So therefore, you want to make sure that all your analyzers that you're using is going to have a zero cal. Set everything first, and then do your cal gases. And your cal gas is calibration, and you want to calibrate your meter at its known interval, and whatever your manufacturer recommendation is. There's so many different types of meters, so make sure you know how to do that. And then you want to field bump test. So known calibration gas, open it up, run through your meter, and then you want to make sure that that is going to be field tested, so all of the sensors will be proven to work. You'll have a audible alarm, a visual alarm, and then you'll have an actual vibration too. Sample from the small hole before opening, and position yourself upwind, so just in case that there is any kind of air coming out of that space that is toxic to you. If you're upwind, meaning the wind is to your back and it's blowing away from your face, then now you can know that once you open that space and the gases come out, it's blowing away from you rather than blowing to you. And then you also want to make sure monitors' batteries are charged. Most of these monitors have rechargeable batteries, so make sure that they are charged. A lot of places can do that overnight. Just make sure that's a good thing. Oh, back to your actual monitoring. And before we get into ventilation, I'm going to show you this over here again. When you're doing this monitoring, you're not letting your meter go down. You want to make sure you have a long enough hose with one of those wands that will collect and channel the gases through the wand, through that filter, into your monitor. So make sure that you're not dropping the monitor, raising it real quick, and try to get that reading. That's not how it works. So you want to actually lower your wand that has it's connected to your meter. Your meter's pump is going to be pumping through that gas and giving you enough time to do 3 purge volumes of that actual hose. So that's a function of math, where basically you're going to go for pi r squared times d, so which is pi 3.14 times itself 3.14 times the radius of that tube, pi r squared. Excuse me, why did I do that? Your radius is what you're going to be squaring, so it's 3.14 times the radius twice, so pi r squared, times the diameter, or excuse me, the depth, and that's pretty much how you're going to get that. So pi r squared times depth, and 3 of those purge volumes is what you're looking for to make sure that you're going to get the accurate reading of each level that you're testing. And now, the next thing that you want to do is make sure that you set up your ventilation, and you're going to do 3 purge volumes again. So know the space that you're in, put in the discharge side of that ventilator, so it's blowing into that space, and purge that out 3 times from whatever the calculation is of that space. So you want to make sure that there's plenty of clean air in there, so there's no real toxic fumes there. So supply or positive pressure ventilation, exhaust ventilation, local negative pressure ventilation, and then positive negative pressure ventilation. That's your 4 different types that you're going to see. And if you are sucking out air from a space and discharging it away from you, you can also be sucking in toxins from any close, it could be a drainage area, it could be fumes from a nearby car or something. So you really want to blow air into a space more than sucking it out. So testing protocol, the confined space internal atmosphere shall be tested with a calibrated direct reading instrument for the following conditions in the order. So here's your testing protocol. Oxygen content first, flammable gases and vapors, and then potential toxic air contaminants. So that's the way that you're going to want to test. We did talk about vapor density. And the PEL is the permissive exposure limit. So you want to make sure that you're well within the permissive exposure limit of any of the vapors or gases that are in a confined space. And then if you get even below that, it's even better. So your confined space hazards for your atmosphere could be asphyxiation atmosphere, something that's going to cause you to suffocate. Flammable, which could cause a fire, obviously. Toxic and oxygen deficiency, oxygen enrichment. So those things are all the kinds of atmospheres that you're going to have. So specifically, you might see you might be exposed to nitrogen, which is colorless, odorless, inert gas. Remember I told you earlier in the lesson, the inerting, it's actually bringing down the percentage of the oxygen. Vapor density means that it is lighter than air because it's at 0.97. It may displace oxygen and cause asphyxiation. Another gas that you might see is methane, especially in a sewer system. Natural marsh type swamp gas, you'll see it. It's colorless, odorless, flammable gas, lighter than air. So again, it's going to be atop of that tank or top of that enclosure. The vapor density is 0.6. And then toxic carbon monoxide, it's colorless, odorless gas, slightly lighter than air, but it's going to be pretty much right around the same breathing zone that you're in. And the chemical is also an asphyxiant. The primary source is incomplete combustion of organic material. And you can see it in gasoline-fueled combustion engines. And then your permissive exposure limits, which are 50 parts per million. And that's of carbon monoxide. Hydrogen sulfides are big, especially with any kind of sewer system. You're going to have that rotten egg smell, but don't get lulled into that because you will have a loss of olfactory senses. So there is what's called olfactory fatigue, loss of smell, if it's too much exposure to hydrogen sulfides. And it is definitely heavier than air, so it'll be in the bottom of that enclosure. So you're going to need to make sure that you blow out some fresh air there. Your permissive exposure limit is 20 parts per million. So in this chapter, we learned a lot about your equipment, your testing protocols, types of gases that you probably see in a permit required confined space, but your space and enclosure is unique to you, so make sure you know exactly what those gases are. We learned about the term vapor density, we mentioned a bunch of times, and then also our testing protocol when it comes to permit required confined space. So when we come back, we'll talk about the globally harmonized system for classification and labeling of chemicals, GHS, and that's a few years old, but just want to make sure we mention it for you.